So now that you've got the basics of how to go through and do an analysis on a rational function, or any composite function actually, just want to go through and look at some of the patterns that you may have noticed happening. And then we're going to go through and do one more example of a sketch of this beast up there, and then some conversation about domains where the thing is above the x-axis and below the x-axis, which is not complicated. It's just one extra piece to add on to this analysis. So I'd like you to take a look at this first one. It has a cubic over top of a square. Now if I were to just sort of cheat and forget everything except the leading terms, I'd have x cubed over x squared. Now when you have something like that, an x cubed divided by an x squared is just an x. And if you were to sketch something that's just an x, that thing looks like a line. So when you went through all the practice problems on the last page, or the ones that you are going to do today, anytime you see one of these rational expressions where there is a higher order in the top than there is in the bottom, if it's one order bigger, right, like a cube is one bigger than a square, then you're going to get linear end behaviors. So when you sketch that thing, you're going to have an end behavior that looks like this, right? So that the function has to, whatever it does in the center, it has to settle onto that line, coming up and down into infinity. If I look at the next one here, this function had a cubic on top and a cubic on bottom. And if I go and I, again, ignore all of the terms except for the first two, then I end up with 5x cubed over 3x cubed. And if I were to actually do that division, I'd end up with, well, an x cubed divides an x cubed. I'm left with 5/3. Well, that is also a line, but it's a flat line. So when you go to sketch this thing, this is the type that has end behaviors that are flat, like a horizontal asymptote, but at a particular value. So I don't know, wherever 5/3 is. Some value up here, so the function has to do this kind of thing as it goes off to infinity. This type here, you notice that the higher order power is in the bottom instead of on top. So if I write that out, 4x squared divided by 5x cubed. Well, if I actually work that out, I end up with a 4 over 5x. Now, this one is going to give us the key piece of information that I sort of glossed over up at the top there. Keep in mind that these are end behaviors, right? They're happening out here on the graph. They're happening when x gets bigger and bigger and bigger. So if you were to choose like a massive value like 10, put that in for x, this thing here is worth 4 divided by 50, which is not very much. If you go out to 100 on your x-axis, this would be 4 divided by 500, which is even less. If you were to take the limit of this as it went to positive or negative infinity, the limit of this is going to go to 0. So how do I want to write that without making it too complicated? I think the point is that a function like this, where you have a higher order in the bottom than in the top, ends up being a flat line on the x-axis. So you don't have to go and do all the fancy long division. you can just look at the structure of the thing, and if you see that it's a higher order in the bottom, then you know that its end behaviors are a flat line on the x-axis. So those are the ones that look like this. Whatever it does in the middle, and then it has to come up and ride 0. That sort of thing. If you see one where the orders are a match, top and bottom, you can simply say that it's going to be a flat line, and you can just take the coefficients in front as the height of that line. If you see that it is higher order in the top than the bottom, you will know that it's linear, and you have to actually execute the polynomial long division to find the equation of that line. You notice I got the x part, and that's okay. But in skipping this, I lost the y-intercept, so I wouldn't actually be able to sketch this. So for this one, and this one only, when you get to be doing end behaviors, you have to do the actual polynomial long division. For types that look like this, you can skip that part and just shortcut to what those end behaviors will be like, based on the structure of the function. Now, this last one down here, I've got a 2x cubed over an x. And we're not actually going to do one of these, but I just want to bring it up to sort of solidify the pattern here. This one, if I take just the leading terms, gives me that, which was 2x cubed divided by an x is a 2x squared. So when there was one extra power in top, I ended up with linear end behaviors. If there are 2 powers available up top, I end up with quadratic end behaviors. Well, that's a pretty exotic function. If I drew that in here, some sort of parabola acting as my end behaviors. So a function like that does something really super exciting in the center, right? It may cross and then have an asymptote and some other asymptote, whatever, but then it becomes this parabola as x gets large, which is sort of neat. Again, don't panic, we're not doing ones like this. But the end behaviors are determined not by the stuff in the center, not by this back half of the equation, but by the first terms in each piece. And back to this idea of x being very large. If I start using numbers like 10 in this equation, the first term of this is worth 1,000. 10 cubed is 1,000. And this is worth only 400. And this is only worth 110. So already at 10 on the x-axis, this term has outpowered everything else in the equation. So once you get past 10, nothing else in that equation really matters. It's defining the center value, and then you move up or down a little bit. Like, these are small adjustments. By the time we get to 20, 20 cubed would be 8,000. So it's starting to dwarf all of these numbers. 10, if you get to 100 on your x-axis, 100 cubed is 1 million, and this would only be worth 40,000. So you can sort of see how that's happening. Okay, I'm going to erase all this mess, and I'm going to know that I need linear end behaviors for this one, and we're going to go through this real quick so you can see another example of how to sketch one. Alright, so we need to get a series of features for this function in order to sketch it, and these features don't change when you go to more complicated composite functions. And I mean, we did this as well when you did the translations and transformations of basic functions. You needed y-intercept, x-intercept, location of any vertical asymptotes, and location of the end behaviors, or horizontal asymptotes, depending on what kind of function it is. So with those 4 features, I should be able to sketch any function. So I just need to start hunting them. I'm going to start with the x-intercept just because it's the most work, because I'm going to have to factor this cubic up here. So I need to find a number that works up there. 1 isn't going to cut it because this is too big. 2 cubed would be 8. 8 plus 16 would be 24 minus 22. That's not going to be big enough. But it might be if I flip this term. I'm going to try -2. So -2 cubed would be -8. That would be 4 times 4 is 16. -2 times -11 is positive 22. Woo! Carried away there. -30. That's -38. That's positive 38, so it's going to work. Okay, so if -2 is a solution to this being 0, then x plus 2 is a factor. So we'll need an x squared. Take that out of the pile. And then I will need a 2x. Be 2x squared plus 4x. Take that out of the pile. -11 minus 4 is -15. It's always exciting when it works out. -15 times this, and that went evenly. Alright, and looking at this thing that's left over, 3 times 5 is 15, and positive 5 minus 3 would be 2. So this thing is going to be x plus 5, x minus 3. Alright, so I'm just going to erase this and write my and if I look at the denominator there, 4 times 5 is 20, and plus 5 minus 4 would be 1. So this is going to be x plus 5, x minus 4. So I've got the whole thing factored, and as soon as I do that, I can see that I have two matching factors. I have this one, and I have this one. So I've just figured out that there's going to be masking, right? Neither this x-intercept nor that asymptote are going to show up, but there will be a hole at x equals -5, right? That's the place where this equals 0. So I'm just going to make a note of that. There'll be a hole when x plus 5 equals 0, therefore that's x equals -5. And if I put the function in there, function at -5, well, that would be -5 plus 2 is -3. -5 minus 3 would be -8. And -5 minus 4 would be -9. So it's at -24 over 9, or over 24 over -9. So therefore, there's a hole at -5 on the x, and 24 divided by 9, it's like 2.5555 or something. .667. Yeah, okay. All right. So found a hole, no problem. now that I've eliminated the masking stuff, I can find where the other intercepts are. So y-intercept at, well, this, we just put in all the zeros, so all this stuff went away. And with minus 30 over minus 20, which is just 1.5. I have an x-intercept for the x value that zeros this bracket and the x value that zeros this bracket. So at x equals minus 2 and x equals 3. I'm going to have a vertical asymptote at x equals 4. All right, and if I check a little bit below 4, so try 3.5, this would be positive, this would be positive, this would be positive. 3.5 minus that would be positive, 3.5 minus 4 would be negative. So on this side it's headed down. And if I go to 4.5, that's going to flip this one to positive, so it's an upward type asymptote. And if I could use this space right in front of my head here to actually do this long division, because I need to do my end behaviors, and because I see that this is a higher order on top, it's going to be a slant asymptote, right? It's going to be one of those lines I have to calculate with the polynomial long division. So I'm going to do that here. Oh, maybe I can fit it in here. Let's see, I am dividing by x squared plus 1x minus 20. And I am dividing x cubed plus 4x squared minus 11x minus 30. So I will need an x, better marker apparently. X times x squared is x cubed plus 1x squared minus 20x's. Take that out of the pile. Minus 9x's plus 3. 3x squared plus 3x minus 60. There's 6x plus 30. Alright, so I can't go any further there, so I've found my end behavior, right? That's it right there. I don't need to write any of this stuff out formally. I can just hack through it and see what I get. So I have left my grid somewhere, so I'm going to go get it, and then we will sketch this. Alright, so if I get my grid on here in green, and I have a y-intercept at 1.5, that's about here, and an x-intercept at minus 2, that's about here, and then another one at x equals 3, that's about here. I have this hole at minus 5, 1, 2, 3, 4, 5, minus 2.67, that's about here. Then I have a vertical asymptote at 4, that's about here. And my end behavior is this line x plus 3. So that starts at 3 on the y-axis and then has a slope of 1. So it goes up like this. And then, to keep from out-clevering myself, I'm going to remind me, that this line only matters after all of the other features. So I don't need it in here, and in here, and in here. I only need it after the last asymptote and before that hole. All right, so in order to sketch this thing, I'm going to look at where my asymptotes were. On the right of this asymptote, it's supposed to be this type, going up to infinity. So if I have to follow this line then, I'm just going to turn around and take off like so. On this side, it's supposed to be an asymptote, you see it there, a downward heading one. I'm going to sketch that in. Now that line has to get up through here, cross this, cross again, hit the hole, and then follow that line. So I'm going to just do that. Up. I'm going to resist the urge to make the y-intercept the maximum, because it very rarely is. And then we're going to follow that line on our way down. There you go. Lovely. So I'm going to erase all this work, and I'm just going to slide the graph down there so that we can talk about ranges where it's positive and negative. Okay, so I'm going to go through and I'm just going to list the features that we found. So we had a hole at, where was that, -5. And then we have an x-intercept at -2. And then we have a y-intercept at 1.5. And then an x-intercept at 3. And then we have a vertical asymptote at 4. At, right, x equals 4. All right, and then we have no other features after that. So I'm just going to go through this list, and I'm going to decide whether the function is above or below the x-axis between those two features. So if I go beyond the hole there, anywhere past here, it's headed down, it's following that line, it's never coming back to the x-axis. So down here, it's negative. Between the hole and that x-intercept, it is also under the graph, so I'm just going to jot in that it's negative there. Between this x-intercept and the y-intercept, it is above the x-axis, so it's positive there. Between the y-intercept and this x-intercept, it is also above, so it's positive. Between this x-intercept and the asymptote, it has gone under the axis again, so it's negative. And between this asymptote and the rest of infinity, it is above the x-axis, right? It's up here and it turned around and it's flying away. So it's never coming back. It's nice and positive. All right. So if I look, then I have this range here where it was below the x-axis, right? Everything from here down. And it's positive in this range. And then it's negative in this section. And then it's positive in this one. Okay. So this little gap here, this is all of the x's that are less than -2. So I'm just going to write that. This little section here is all of the x's that are between -2 and 3. Note that I'm not using the equal sign. I'm not using the equal sign because at 3 the thing is worth 0, which is neither positive nor negative. So you use your greater than and less than, not the greater than equal sign. This section here is everything between 3 and 4. And this last section here then is every x that's greater than 4. So in the practice problems, you're asked to identify all of the domains where the function is positive and all of the domains where it's negative. So if I were to just summarize that up here, positive on these domains. Well, I just have to go through the list here and pluck them out. So it's this one. -2 is less than x, which is less than 3. And this one, where x is greater than 4. Follow up to that is it's when is it negative? So it's negative on, I don't need to write these domains, you can infer what that means. Negative on this one, x is less than -2, and this one here between 3 and 4. So that's the last little chunk of information for rational analysis. So you should be able to hack through the next practice set, which has some masking, some that do not have masking, some that have slant asymptotes, some that have 0 as their asymptote. And you can use the quick tricks in order to work those things out if you'd like. You maybe had already started noticing those patterns, and that's okay. Basically, we're done this unit, so good luck.